Hello, guys. Welcome back to Meso African Motives. Still on engineering science and three, working on revisions. In this case, we've got the question on moments that we are going to focus on. So we are given the first part of our question on 2.1 to state two conditions for equilibrium for a number of coplanar forces acting on the same point. So take note, the coplanar forces that we have, they're acting on the same point. So we need conditions that will make them to be in equilibrium. All right, so what are the conditions that we have? All right, the first part that we need is the sum of the anticlockwise moments is going to be equal to the sum of the clockwise moments. All right, so meaning to say, if you add what you have for the anticlockwise moment, it must be the same as the one for the clockwise moments. All right, and also the sum of the upward forces must be equal to the sum of the downward forces. So meaning if we are adding the upward forces, they must be equal to the sum of the downward forces. That is the condition that we are given in this case. All right, so that was our first part of the question. Now we are given on the other part of the question that given a light horizontal beam A, B, C, D, E, F of a uniform cross-section loaded as shown. So this is a light horizontal beam that we have. So we are given on 2.1 to calculate the reaction of the supports B and E. That is 4 marks for that. Okay, so I'm going to work this one out from the second part on this page here. All right, so this is our diagram that we are given. So what you need, guys, is to analyze from the diagram or the beam that we're given, what is it exactly that we are given? All right, let us start from the point A. Direct at point A, we are given a distributed load of 80 kilonewton per meter that is affecting from point A up to point C, where we've got a 50 kilonewton. So that means for the 3 meters, the 2 meters plus 1 meter, which is 3 meters. So the 8 kilonewton per meter is going to affect the 3 meters from A to C. So if you multiply by 3, that is, we are going to obtain 24 kilonewton in this case. So the 24 kilonewton now can be separated between these points from A to C. That is between the 3 meters. So if you separate it between the 3 meters, it means we are going to have it as 3 meters divided by 2, which is going to give us 1.5 meters. So what we are going to do is to separate 24 kilonewton between 1.5 meters from A to C. So as we can see, guys, 1.5 is actually less than 2 meters. 2 meters is from point A up to B. That's where we have the 2 meters. So meaning to say 1.5, we are going to have it lesser, just below 2 meters. And also it must be greater than 1 meter. So we are expecting somewhere here. All right, so let me just put it somewhere here. So at this point, I'm going to have it as a point load now of 24 kilonewton. So this is now 24 kilonewton. All right. So like I said, it is going to be separated between 1.5. So 1.5, that is something less than 2 meters. So you're going to have 1.5 here, 1.5 meters from this point A to this point load that we now have, and also 1.5 up to the 50 kilonewton here. We are also going to have 1.5 meters. So if you note, there's a certain distance that we are not having in consideration from our diagram here. That is the distance between these 2 points here from the point B. Take note, the B that we are given on our diagram is at this point. That is our support here. So there's a distance between these 2 points, our support, and the 24 kilonewton, this one that we calculated. There's a distance in between that we are seeing here. There's a difference that we are going to see here. So what is that difference that we have? So we are going to subtract. Remember, I said from this point to this point is 1.5. So if we subtract 1 from 1.5, we are going to have 0.5. 1 minus 1.5 minus 1, we are going to obtain 0.5. That means in between here, there is a distance of 0.5 meters in between. There's a difference of 0.5. All right. So that is what is important that you're supposed to note on your diagram. Okay. Anyways, let's check. From C, everything is fine. We just have our point load here, another point load. So here, this point load, it's a special point of 30 kilonewtons. So we just write, okay, this is F. So let us just write this as point G. It's a special point because it's a point load, all right? Then at D, we are having also a point load at D. Now we are starting a distributed load again, this time of 12 kilonewton. For how many meters? From D up to F, that is where it is affecting. Meaning to say it's affecting for the 5 meters we are having here. So we are going to multiply just like the previous part, 12 kilonewton per meter times 5. This is going to give us 60 kilonewton. So we are going to separate 60 kilonewton from D to F. That means we are going to divide the distance 2 plus 3, which is 5, divided to 2, which is going to give us 2.5 meters. So as we can see, now we are going to have it as a point load of 60 kilonewton separated between 2.5 meters. 2.5, definitely it's greater than 2 meters, but less than 3 meters. So we are going to have, because from this point, from D to E, that's where we have 2 meters. So 2.5 can be somewhere here. Okay, so your diagram, sometimes it might not make sense because of how it will be drawn, but what makes sense is the information that you're indicating. All right, so this will be a point load now of 60 kilonewton. All right, so we are going to have this as 60 kilonewton. Like I said, separated between 2.5 meters. So between this point to this point, we are going to have 2.5 meters. Then from this point up to point F at the end, this is where we have our point F. We are going to have also 2.5 meters. All right. So these are the distance that you're going to have. And as we check again, there's a distance that we have in between these two points that we have. The 60 kilonewton and the point E, there's a distance that we have in between here. So how are we going to find it? Just like the previous part here, there's a distance that is in between these 2 points. All right. So how are we going to have this distance? We simply subtract 2.5 from D up to 60. So that's 2.5 minus D up to E, which is 2 meters. So 2.5 minus 2, that will be 0.5. So in between here, there's a distance of 0.5 meters from E to this point. It's very, very important for you to note that. So according to our adjustments that we have on our diagram, it will be easier for you just to note these. Okay, so it is not supposed to take much of your time to indicate this. It's just it's actually nothing, guys. It doesn't take you much time to indicate this. Then after you've indicated, it's now easier for you to calculate whatever that you want from your diagram. Okay, so as we said, we want to calculate the value of B and also E. So I'm going to start by taking moments about E. All right, so taking moments about E. So from our formula, we understand that from our laws of moments, we can simply say, depending with the direction that you're going to take, but as you can see, B as it is going the direction to E, because you're considering if you take moments about E, you'll be calculating the value of B at that moment. Okay, so like I said, let me just have B properly on this part. I can't remove this, but let me just write it properly here so that we understand. This is where our B is. This is a support. It's at this point. So B, as it is moving to the point E, it's having this direction, which is a clockwise direction. So we're going to consider the sum of the clockwise moments being equal to the sum of the anti-clockwise moment. Depending with which side you want to start with, you can even start with the anti-clockwise to the clockwise moments. All right, so let us consider B. What will be the distance now from B up to E? So you want the distance now from the point B to E. This is the movement that you're going to take. All right, just like this, from B up to E, like this, up to this point. So we want to know the distance between. So let us consider here, we've got 1 meter, we've got 1.5, we've got 1.5, we've got 2 meters. So these are the distances that you're going to take up to the point E. So that will be 6 meters. That's 2 plus 3, which is 5, plus 1, which is 6. So you're going to have, remember, your moment is force times distance. So that will be force times distance, which is B times the distance of 6 meters. So you have to check, do you have anything that is related to E in the clockwise? Okay, this is where we have our point E, our support. So let us check whatever that is going in the clockwise, okay? So if you check these other moments that we have on this side of E, on the left side, they are moving this way, which is anti-clockwise. The D moving this way, which is anti-clockwise. So everything on this side is moving in the clockwise. But if we check the point, I mean the point loads, if we check all the point loads which are this side, they are moving in the anti-clockwise. But if we check this point load that we have now, because remember, we calculated this and we said now it's 60 kilonewton. So the 60 kilonewton moving back to E, it's moving this direction, which is a clockwise direction that we are maintaining. All right, so that means this is a clockwise. We are going to add it to this point. So what is the distance between? That's 60 times 0.5. So you see that distance that I was talking about, it's very, very important for you to note it. So now we are going to have 60 times 0.5. All right, which is equal to the anti-clockwise now. So considering now at E, we said all these point loads which are on the left side, they are moving in the anti-clockwise. So meaning we are going to have 20 back to E. That's 20 times E, which 20 times 2, which is the distance. So we are going to have 20 times 2 plus, all right, we move on from our values here. After 20, we've got 30. So 30 back to E, this is what you're considering. That's 1.5 and 2 meters, which is 3.5. So we're going to have 30 times 3.5 meters, which is our distance, plus we move on here. We've got 50 kilonewton. We've got this 50 kilonewton back to the point E. So that will be 50 times the distance. If we add 2 plus these 3 meters, we are going to have 5. So that's 50 times 5. Plus, we still have another one, 24 kilonewton here. But on 24, take note, we are going to add 2 plus this one is 5. 2 plus 1.5 plus 1, which is 5. Then if we take note, we have got from this point up to this point, which is 1.5. So we are adding 1.5 to this 5 meters. We are going to add 1.5. So this will be 6.5. So that's 24 kilonewton times the distance, which we said it is going to be 6.5 in this case. All right. So this is how we are supposed to take our moments. So everything is there. We have presented everything. So now we can combine and see what you're going to have. All right. So that's B times 6, which is going to be 6B plus 60 by 0.5. That will be a 30. And we combine everything on the right-hand side, we are going to obtain 551. So that's 6B is equal to 551 minus 30. All right, so 6B is going to give us 521 in this case. If we subtract proper, then you can divide by 6 both sides. So that is going to give us the value of B. So 521 divided by 6 is going to give us 86.8 3. Okay, that is to 3 decimal places. All right, our answer in kilonewton as the units that we have before. So this is how we can calculate using our laws of moments in this case. All right, so meaning to say we have the value of B in this case, this point at B. All right, so this B is now presented as 86.833 kilonewton. All right, which is fine. So now from this information, what we are going to do now is to take moments about B. That is the one that we just calculated. Now we are going to take moments about that point B. All right, so I'm going to have it here. Okay, so this is how we simply have these questions, guys. It's not like it's too much. It's just you just have to work with more revisions, more question papers actually. All right, so let us check what we're gonna have if we are taking our moments about B. So this time it's about the point B. All right, so about the point B, let us check now the movement of E to B. So actually, as for me, I prefer working with the point that you're calculating. Since I'm calculating E, I'm just consider how does E move back to B like this. This is the direction that we are taking. If we check, this direction is anti-clockwise. So meaning to say, I'm going to refer this as the sum of the anti-clockwise moments equal to the sum of the clockwise moments. All right, so let us see what we have. E, as it moves back to B, that is force times distance. So it's going to be E times the distance from E to B is the same as the one that we got before from B to E, which is 6 meters. So you add everything. So that's E times 6. So let us check at B. What else are we having that is in the anti-clockwise? All right. So if we check from B, I want us to see something here from the point B. All the point loads that we have on the right side of B, they are moving this way. They are moving this way, which is the clockwise movement they are taking. But if we check this other side, the left side, we have got 24 kilonewton moving back to B. It's moving this way, which is anti-clockwise. So meaning to say all these on the right side, they are clockwise. All right. Then the 24 kilonewton is on the anti-clockwise. So you're going to take the 24 kilonewton back to B, and there's a distance of 0.5 in between. So that's 24 times 0.5. So you see that distance that I was talking about is very, very important for you to note it. All right. So we are going to add, since it's part of the anti-clockwise. So you said 24 by the distance of 0.5. All right. So that's what we have on the anti-clockwise. And we say the other forces that we have, the other point loads, all these point loads, they are moving clockwise to B. All right, so let us start with the nearest one, which is the 50 to B, that is at C. So 50 back to the point B, that's where we have got the 1 meter. So that's 50 times 1. So we are going to have 50 by 1. All right, plus we still have another one. After 50, we move on to the point G. At point G, this is 30 kilonewton. So it's 1 plus 1.5. So that will be 2.5. So that's 30 times 2.5, the distance between. So 30 times 2.5. All right, plus we still have 20 here. So we ask ourselves from 20 up to B, what is the distance that we are going to take? So 1.5, 1.5, that's 3. 3 plus 1, which is 4. So we are going to have 20 times 4, the distance. All right. Plus, we still have another one, the 60 kilonewton here. So on the 60 kilonewton, we consider, we said from B up to D, it's 4 meters. So we add 2.5. From this point up to this point at 60 kilonewton, it's 2.5. So 4 plus 6.5 is going to give us 6.5. So that's 60 times 6.5. So that's force times distance, the force of 60 times the distance, 6.5, back to the point B. All right, so this is what we are going to have. So from this, we can calculate the value of E. That is E times 6. We are going to have 6E plus 24 by 0.5, which is 12. And we add everything on the right-hand side, which is going to give us 595. All right, so that's 6E transpose 12 to the other side of the equation so that it can be a negative. So that's 595 minus 12, which is 583. So we are going to have 583 divided by 6 both sides. We obtain the value of E. All right, so this is going to give us the value of E, which is going to be 97, 16, it's going to be 1666 and so on. So to 3 decimal places, that will be 167 kilonewton. All right, so we have the value of E in this case from our calculations. We managed to obtain the value of E at this point, which is 97,167 kilonewton. All right, so it is very, very important for you to also test your answers to say if the sum of the upward forces is equal to the sum of the downward forces. Okay, so that is what we had in this case, guys, as we can see. All right, so let's consider the other part of our question. All right, we had another part of our question was to calculate or to draw, 2.2, draw a shear force diagram using a suitable scale. Show all the main values on the diagram. All right. So just because here I'm not having a nicer part that I can use, I'm just not going to consider this part of a suitable scale. But what you simply need is to tell us what are you using for the horizontal, for the vertical, also the scale that you are using for the horizontal. You just name according to your choice. All right. So I'm going to show you what is important, which are the main values that you need. Then you choose your own scale that you're going to use to draw. But here I'm just going to use the main values. All right. So remember that we calculated the forces. We calculated the value at B here. We also calculated at A. At B with 86,833. That was 833 kilonewton. And at E, we calculated this with 97,167 kilonewton. All right. So from our shear force diagram, what we need, I'm just going to use this part. I'm going to extend each part from A, B, C. Remember, we say this is going to be our point G. We extend all these points that we have, which are the major points that we are given on our diagram. These are the major points, so you extend them. All right. So let me just extend this part first. All right, so this is what you're going to have. As you can see, you've extended from A, B, and each and every point. All right, so what you're going to do is you refer back to the original diagram. All right, so this was our original diagram, actually. All right, so you're going to refer back to the original diagram, and each and every step has to be followed from our original diagram in this case. All right, so let us start with what we have at point A. We do not have anything at point A, that's at 0. So that is the point at 0 kilonewton. Then if we check from A to B, let us check what is happening. You work with the major points. So from A to B, this is a major point, So from A to B, there's a distributed load that is affecting for 2 meters, that is from A to B. All right. So this time you're going to subtract that from, because remember we started at 0. So you're going to subtract every time a distributed load, you subtract, but you multiply to the distance affected from A to B. So from A to B, that's 2 meters. So it's going to be 8 by 2. So that's 8 by 2, which is 16. So this is going to give us negative 16. So we are going down negative 16, that is below the horizontal line, this one. Above it's positive, below it's negative. So meaning to say our negative 16 is below. And also you have to take note, this is a distributed load. Every time you present a distributed load, you present it with a slanted line like this. All right, it's going to be a slanted line. All right, so like I said, according to your scale now, you're going to mark negative 16 according to your scale in between these 2 points A and B. So maybe under B here, this is where I'm having my negative. So you mark this according to your scale. So let's say this is where we have got our negative 16 kilonewton according to our scale. So we are going to join from 0 to negative 16. So like I said, this is going to be a diagonal line. Even from your diagram, you can see that once you are joining this, actually you are producing a diagonal line like this. All right, so that's from point A to point B. All right, so this is how we're going to present from 0 up to negative 16. So which is important for you to note according to the scale that you have presented. All right, so let's see what we've got at B. Now at B, we are given a support which is going up every time you present a support. Remember, I said you add a support, you add whenever you are dealing with a support, you add, and always it's a vertical line going up. So you're going to present it going up. All right. So we are going to add to the value that where we are now, according to our point, we are at the point negative 16. So at negative 16 kilonewton, that's at this point at negative 16, we are going to add the support, which is going up of 86,833. So if we add this we are going to obtain 70,833. That's 70,833 kilonewton, which is above, because it's a positive, so it's above the horizontal line. So according to your scale, you just approximate according to your scale. Maybe we are talking about a point which is somewhere here. So this is going up, straight up. So maybe that's a point somewhere here. That's where we are going to have our 70,833 kilonewton. So you join, it's a vertical line. This one is a support, so it goes up straight. So you're going to join that, okay? These points from -18 up to this point like this. All right, so this is how we're supposed to have it. Our major point, which is at this point here. All right, so that is what we had. Then we move on. Again, like I said, you refer to the original diagram. Now we are at B. From the point B to the point C, again, we are having a distributed load. It's affecting from B to C for 1 meter. So it's going to be 8 times 1. So remember, a distributed load, we subtract just like the previous part. So meaning to say, at the value of 70,833 where we are going to subtract 80 kilonewton per meter affecting 1 meter. So this will be 8 times 1. So if we subtract this, we are going to obtain something like 62,833. That's 62,833 kilonewton. And this is a distributed load, so it's going to be a slanted line like this, okay? But automatically, if you present it properly on your diagram, the point is going to just show up itself, all right? How you're going to present it. So we need 62,833. So according to our scale, maybe our 2,833 is at this point. So you're going to mark this point 62,833. So you join from this point up to this point. So as you can see, automatically it forms a slanted line. But you're also supposed to know that once you're dealing with a distributed load, it's a slanted line that you're going to have like this. All right, so this is what you're going to have up to this point. All right, so this is how we're supposed to have it according to the scale that you're using, guys. Okay, so we are now at C. So let's check what we have at point C. At point C, we have got a point load, 50 kilonewton, which is a point load going down. Every point load subtracts, it's a negative, and it's presented with a vertical line. So you subtract that one. All right, so that means we are going to subtract from 8,833 kilonewton where we are at this point. We are going to subtract 62,833 minus 50 kilonewton. So if we subtract 50, we are going to obtain 12,833 kilonewton. So this is going down a vertical line, 12,833, which is, we mark our point. So 12,833 is approximately at this point, because it's above the horizontal line, is a positive value. So we are going to have it above, maybe somewhere here. All right, so we are going to join these 2 points up to this point here. All right, so if we join this, this will be where we are now at 12,833. So this is at 12,833 kilonewton. That's at this point here. All right, then we move on. Remember, we are at C now. So from C, we move on from C up to G. From C to this point that we referred as G, remember we said there is an important point here. There's just a normal distance, 1,5. There's nothing that we have. So how do you present that one? Where there's nothing, you just present a horizontal line. So we are going to just join a horizontal line. In this case, we are just going to have it a horizontal line from this point at C up to, from C up to G, meaning to say for that distance that we have of 1,5, we are just going to join straight. All right, that's from this point here. All right, from this point up to this point at G. That's where we are going to have our 1,5 at. All right, so it's very, very important to note that. So meaning to say, if we are moving straight from this point up to this point, we are still at the value of 12,833 at this point here, where we are at this point. We are still at 12,833 because it's it's the same distance that we are having. It's a horizontal line. Nothing has changed. All right. So now at G, what do we have at G? If we check from our diagram, at G, there is a point load. And I said every point load subtracts. It goes down, it subtracts, and is presented with a vertical line. So we're going to subtract 30. Where we are at this point, remember we are at 12,83. So let's subtract and see what you're going to have. At 12,833, we subtract our point load where we are at 30. So if we subtract 30, we are going to obtain negative 17,167. All right. So negative 17,167, it's below the horizontal line. Take note, we are at G here. So it's below the horizontal line because it's a negative. And remember, it's a point load that we are talking about. So it goes down straight. It's a vertical line. So we are going to indicate at negative 17,167. Approximately, it's supposed to be a little bit below this negative 16 according to your scale, maybe somewhere here. All right, so that's where we have our negative 17,167 kilonewton. All right, at this point, so we are going to join, like I said, this one, we are going to join it straight. It's a vertical, with a vertical line since it is a point load. All right, so it's going down straight to this point. All right, so this is where we are now at this point. All right, so that was at point G. Now let's note what is happening from the point G. Let's check what is happening from our point G in this case. All right, from point G up to D, we've got nothing. It's just a normal distance of 1,5. So just like the previous part, we just draw a horizontal line for that distance of 1,5. That's from G to D. So we are going to have this as a normal part. All right, so you're just going to have a horizontal line straight from this point up to the point at D, like this, straight to this point. So meaning to say, we haven't changed anything. If it is like this, we haven't changed anything. We are still at negative, we are still at negative 17,167. That is what is important in this case. All right, so let's check what we have now after the point at D. All right, so now if we check here, what's gonna happen from D, that is where we are. Okay, let me just try to adjust this side. This is the major part that we want here. So now D, from the point D that we are given to E, remember I said step by step. All right, so we move from D to E now. So we want to move to the point E. What do we have from D up to E? We have got a distributed load affecting from D to E for 2 meters. So we've got a distributed load in this case. All right, so meaning to say we are supposed to consider that. All right, let me check. Okay, I skipped something here. All right, sorry for that. The 20 kilonewton, I'm seeing that this part I didn't consider. So let's not, we are still at D. All right, I saw this blue thing and saw that I have worked it. All right, so from D, we direct at point D. We have got the 20 kilonewton. This one, we didn't consider it. So it's going down. So we're going to subtract that one. Remember what I said, whenever you are dealing with a point load, you subtract. So meaning to say at negative 17,167, we are going to subtract 20, which is going to give us negative 37,167. All right, so negative 30,167 according to our diagram is going to be down. Remember, it's a point load, so it's going straight down. All right, so let's just say according to our scale, I don't know where you're going to have it, maybe somewhere here. You're going down. Remember, it's straight down. It's a point load, this one. All right, so I actually skipped this one. All right, which is something that you are supposed to avoid in exam. Actually, this diagram had a lot of things. That's why. All right, so here we are going to have this as negative 37. So that's negative 37,167 kilonewton at this point. All right, so that's it. We have considered D now. All right, so D is now involved. We have considered our 20 kilonewton. Now we move from the point D to E, from the point D up to E, that there is a distributed load affecting for 2 meters. So meaning to say, we are going to have our slanted line like before, but this time for 2 meters. All right, so we are going to subtract. That's from negative 37,167, where we are, we subtract 12 kilonewton times 2 meters. So it's going to be 12 times 2 for the 2 meters that we're talking about. So this is going to be at negative 61,167. Okay. Remember, it's a distributed load, so it's going to be a slanted line like this, okay? So direct under the point which goes straight at E, this one, we are going to have at negative 61,167. That's approximately, according to you, our scale, maybe we are going to have this at this point here. All right, just approximately there. That will be where we are having our negative 61,167 kilonewton. All right, so we join this part. All right, so we're going to join. Remember, it's going to give us a diagonal line or a slanted line like this. All right, so these are the major points that you are going to consider. Okay, let me just join. So we are going to join these 2 points. All right, so these are the major points that you're going to consider or to have in this case. All right, so let's see what you're going to have later on. All right, so now at E, let's see what are we having at E. We moved this one for the distributed load. But if we check now at E, direct at point E here, we have got a support at E. It's a support going up. That is 97,167 going up. So we're going to consider that. We add a support. Remember, I told you a support you add. So at negative 61,167, we are going to add our support. This is where we are, guys, at negative 61,167. So we add our support, which is at E, which is 97. So we are going to add 97,167. So if we add this 97,167, we are going to obtain 36 kilonewton. So that's 36 kilonewton. It's a positive. So take note, guys, 36 kilonewton, it's a positive. So meaning to say our horizontal line, the one, our vertical line, the one that we are going to draw to represent a support. Remember, we are supposed to have a vertical line going up. So this line is going up to the positive. It means we are going to cross the horizontal line. So maybe according to our scale, 36 is approximately is going to be below 62, above 12, but below 62. So maybe somewhere here, according to your scale, guys, like I said, please, you are supposed to consider the scale there. I don't know, maybe your scale that you're using, but it's supposed to be in between those 2 points. All right, so that is it. We are going to join up to this point. All right, so this is what we have up to this point. All right, so this is our presentation that we are going to have at the end. So like I said, this is going to be 36 kilonewton. So we are at 36 kilonewton. All right, so that is, we have considered the point E. Now we move on from E up to F. This is the last stage from E up to F. It's a distributed load again, affecting for 3 meters. So it's going to be 12 times 3. So we subtract at 36 kilonewton where we are, we subtract 12 times 3, which is going to give us 0. So this is going back to the horizontal at 0 at this point. So if we join, like we say, it's a distributed load, giving us a vertical, a slanted line if we join. So that is what you are going to have at the end. So to show that this is actually in equilibrium, that is why it closes at 0 kilonewton. This shape is supposed to close. So if it is hanging up, it's not closing, then it means somehow something is happening, something is wrong. All right, so these were the major points that we're supposed to have. So it was actually a lot. Yeah, this diagram, it was actually a lot, but this is what you're supposed to consider according to the diagram that you're given. Take note on your distributed load, this part, the point, you take it step by step from A to B, from B to C, from each and every point must be considered on your diagram. So if every part is considered, then you know that everything is okay. So that's what we had, guys, from our question on moments from Mason African Motives. Till we meet again.